Welcome back to a course on multivariable calculus. We are talking about the concept of multiple integrals. In this lecture, we are going to talk about double integrals over general regions. Actually, in the previous lectures that is in the previous classes, we have seen double integrals over rectangles, right? Whenever we talk about single integrals, so single integrals means we are going to take things in two-dimensional thing. Okay, that is we will have a function of one variable, right? Whenever we take a function of one variable, a function may be something like this. We will integrate over some interval, be it open interval or closed interval. It is going to be some interval, right? So this is the only possible thing we can take. Else we may integrate over this thing. If these two are distinct, then the integration over these union of these intervals will be what? The integral over this interval plus integral over this interval. So anyway, there we are dealing only with intervals. Whereas if you here we are talking about integration in two variables. Am I right? So if this is the case, it is not always necessary that we have to talk about the integrals over rectangles. It may be any general shape. So that is how we are extending our ideas. So we are extending our ideas of double integration to any general thing. Okay, if we have a general space, like just a minute, let me change it to laser pointer so that you can see it in a clear way. So if we have a general region like this can be put inside some rectangle like this. Okay, once it is put inside some rectangle like this, then we are able to do the integration over this region by extending the function to the rectangle. So how are we going to extend it to the general function? So how do we do it? It is quite simple. So if the function f of xy is defined on this region, okay, you have some function, okay, actually this is where you have your d, okay, and you have some surface over this like this, and you will have to, okay, suppose if this is your surface, then you have to identify the space it takes, and you'll have to find out the volume. That is how the integration works, right? Now we have identified a rectangle containing this region, and we are going to integrate over this rectangle. How are we going to do it? So this function f behaves f itself whenever you take points inside this region d, and is 0 outside this region d. So that is how we define this function, and integral over d f of xy, and the area of with respect to the area is same as that of integral over r big F of xy over the area. So this is the ideology by which we will do for general regions, right? So exactly the one that I explained is specified here, and the diagrammatic things are specified here. Here, the region D may be of type 1, okay, or type 2. What is type 1 and type 2? Here, your x value is fixed between two values. Okay, your x takes value between these two values, and y takes between these two functions, and they are functions of x. Let us see here. Here, if you see in the is diagram 5, you may very well notice that your x value ranges from a to b, whereas your y value ranges from this curve to this curve. Okay, I think I'll go for highlighted. If you see here, your y value ranges from this to this. Okay, and here, coming to the second picture, you may very well see that here your y value ranges from this curve to this curve, and here this curve to this curve. In all these three things, your x value ranges from a to b, some fixed finite quantities. Fine. These kind of regions are called as type 1 regions. In order to evaluate the in order to evaluate the type 1 regions, what do we do is that this is what initially we have it for rectangle. Sorry, actually we have converted the general region to a rectangle. So what we have is uh, I think I shall better highlight things. So if you see, this is what we have. So integral over the region D is same as that of the integral of big F over R. So whenever we talk about integral over R, what do we have over these things? CD is with respect to Y and AB is with respect to X. So this Y has to be converted to some functions. Okay, actually how did we find that C and D? Let me tell you now. If this is going to be our thing, then these kind of rectangles we take. Okay, actually we don't go to, yeah. So this is the rectangle that we take. So if we are going to take rectangle like this, then the rectangle has to be converted to curve. So the C and D changes to this and this. Actually this is your C and this is your D. Okay, your C changes to this curve and D changes to this curve inside D. Okay, using that idea, integral c to d f of x y dy becomes integral g1 of x to g2 of x big F of xy big F of xy dy, and that variable is what? That variable is integral g1 of x to g2 of x small f of xy dy. Okay, just a minute. Yeah, so this is what we have. So using those ideas, we have converted this one, and your integral becomes what? Integral a to b integral g1 of x to g2 of x f of xy dx dy. This is for type 1. So what is type 2? Type 2 means here your y value is fixed and x value varies between two curves. Okay, these two are some type 2 regions. And here your integral, using the same idea, you can extend this. Using the similar arguments, you can extend the idea, and here you may very well see that first we are integrating with respect to x and then we are doing it for y. Okay, now we are entering into the problems. Here calculating these problems is quite straightforward, so I will give more focus on explaining the ideology behind this than on explaining the steps involved in doing this integration. Okay, here we are asked to evaluate this integral where D is the region bounded by the parabolas. Okay, first of all, try to plot these parabolas. Okay, so hope from the knowledge that you have gained in your higher secondary, you are able to plot the parabolas. So I am not focusing into it. Just try to plot the parabolas, and you can very well see that which is the lower one, which is the upper one. Okay, even if you don't know how to plot these parabolas, okay, let me give you the other way of idea. Okay, that you can try and implement. First of all, here decide whether they are intersecting or not. Yes, of course they'll intersect, so that we are going to get some common region. Okay, actually here this in this diagram you are seeing a two-dimensional thing. Okay, so this two-dimensional thing is going to be in, when you do the actual integration, your common region would be something like this. Okay, you have x plus 2y. This is another plane. Okay, so this is what you will have to calculate, something like this. uh, okay, that is not plotted here, but anyway, that is the ideology that we have to do. Fine. First, equate the given curve so that you can find out the point of intersection, and those point of intersection is going to be your x limits. Okay. Once you plot the curve itself, you can very well see that this is a graph of type 1. So we'll have to identify the x points, and those points are the points of intersection. So if you just equate these two things, that is 2x square equals 1 plus x square, and upon solving this, you just take this x square to this side, so it becomes 2x square minus x square. Actually, 2x square minus x square equals 1. Therefore, your x square is 1. That tells you that your x is plus or minus 1. Okay, from this you are unable to identify some region of type 2, so we'll stick to type 1 itself, and this region is this. Here we'll have to identify which one is above, which one is lower, for which you have identified the x limits, right? First identify the x limits. Once you identify the x limits, between these two limits identify any of the point. So between minus 1 and plus 1, we can identify 0, right? So substitute 0 in these things. Y of 0 in the first thing is going to give you 0. Then in the second thing, if you do so, it is 1 plus 0 square, which is 1. So if you take this one as y1 and this two as y2, okay, this one as y1 and this one as y2, you may very well see that your y1 value is smaller than y2. These are the points of intersection, which means between minus 1 and 1, your y1 is going to be the lower one and y2 is going to be the upper one. That you can conclude. Okay, once you do these things, you can very well write what is your d. So you have written down the d. So integral dx plus 2y dA is going to be integral minus 1 to just a minute, I'll make a laser pointer. Yeah, so integral minus 1 to 1, integral 2x square 1 plus x square, and then you are just doing first you are integrating with respect to y. You will have to treat x as a constant and do the integration, substitute the limits, and the rest is merely the calculations. That calculation you can do. Okay, here let me give you what, yeah. So in this example, uh, first we had 2x square and 1 plus x square, right? So I have already inputted the functions that we are dealing, and that is why I have things already. So this is the thing that we have. This is one point of intersection that intersects at 1 comma 2, and this is another point of intersection that is minus 1 comma 2. So minus 1 to 1 is the point, and here we are seeing the things happening. This is done in 2 dimension. When we go to things in 3 dimension, so y is equal to 2x square. So you may very well see how it behaves, right? And y is equal to 1 plus x square. Here you may see the 3 dimension version of the thing that we have seen in 2 dimension. Okay, we are this region is the common region with which we'll have to integrate x plus 2y. So here, if you just try to rotate it and see, you may see some region. Actually here you can find that region. Okay, in here you have the common region. Okay, I think if I can download this image and insert it in the PowerPoint, it will be easy for you people to see. Yeah, so I have done, and just a minute. So let me insert that. Downloads, I have this. So here let me try and plot the common region. So here it is going This is in 3 dimension. Okay, that you can see, I hope. Okay, you have something like this. So this is the volume of this region only you are finding. So that is what is done just by doing the integration thing. So this is the ideologies behind these things. The next problem that we are going to see is here. You may very well see, we are asked to find out the volume of a solid that lies under the paraboloid x square plus y square equals z, and the region y is equal to 2x and y is equal to x square. First, let us do the diagrammatic part and come back to the calculation. So first we have y is equal to 2x and y is equal to x square, I hope. So this is the common region. The points of intersection is 0 comma 0 and 2 comma 4. Here you may very well see that either you can take this way. Okay, your x varies from 0 to 2, you may take this way, or your y varies from 0 to 4, you may take that way as well. Okay, either way you can take. If you fix 0 to 2 for x, your lower curve is what? Y is equal to x square, and your upper curve is y is equal to 2x. If you decide to go with type 2, your left curve is y is equal to 2x and the right curve is y is equal to x square. So whenever you are dealing with curves in y axis, okay, with respect to y you have fixed the values, and with for x you are trying to find out the curves. In the sense, you will have to find the left and right. Okay, if it is for x you are fixing the values, and for y if you are trying to find out the curves, you will have to find out identify the lower and upper curves. Now let us go and see these things in 3 dimension. Let me turn off these things. Y is equal to 2x, which is a plane. Y is equal to x square, which is something like this. So you can very well see the common region here, and this is what we have. So if you want, I can turn the color of the shape. Blue is not used, right? So let us go to blue color. Sorry, I have changed color for something else. I don't know why it is not changing. Okay, anyway, here you may very well see that this is here is your common region, and here you are enclosing some part of this thing, and only for that we will have to identify the actually let us try to fix things in a positive sense. Yeah, here. So this is where we have the common region, and this part of the solid for which we'll have to find out the volume. Okay, I think here we may just do it by the direct things. So either you fix this way or this way, it is up to us. As I said, let me do it by type 1. So while doing for type 1, my region D is going to be the collection of points in R2 satisfying what? X varies from 0 to 2. 0 less than or equals x, less than or equals 2, and y varies from what? X square to 2x. So x square less than or equals y less than or equals 2x. Okay, this is what we have. So integral over d x square plus y square is integral 0 to 2 integral x square to 2x x square plus y square dy dx. When you integrate with respect to y, you are going to get x square y plus y cube upon 3 over x square to 2x dx. So this is integral 0 to 2, and when you give 2x in the place of y, you are going to get 2x cube plus 8x cube upon 3 minus x power 4, and when you do here it is minus x power 6 upon 3 dx. So this is what, when you integrate with respect to x, you are going to get 2x power 4 upon 4 plus 8x power 4 upon 3 multiplied with 4 minus x. This is what, and minus x power, sorry, actually x power 7, right? Yeah, x power 7 upon 3 times of 7 over this limit. So this would give you, actually 2 and 4 gets cancelled, 8 and 4 gets cancelled, that's it. So it is x power 4, 2 power 4 is 16 upon 2 plus 2 times of 2 power 4 upon 3 minus 2 power 5 is 32 upon, actually we can write it 16 directly. So 32 upon 5 minus 2 power 7. 2 power 7 is 64, 128. 128 upon 21. If you actually, it is 16 upon 2 is simply 8 plus 32 upon 3 minus 32 upon 5 minus 128 upon 21. So when we take the LCM, it is going to be actually 7, 3 and 5, 35, 105. So it is going to be 105. So we'll have to multiply 105 plus 32 into 21. Is it 21? No, 35. Yeah, it is 35, yes. Minus 32 times of 7 into 3, 21, minus 128 into 5. So this is what we have to do. I think I don't need to spend much time on doing this calculation, that you can do. Just a simplification and that gives you the answer. And the other way of doing it. So this is one way, you just try to complete the simplification. And the other way is, uh, your D may be written as the collection of points in R2 where the y value is fixed between 0 to 4, right? So 0 less than or equals y less than or equals 4, and your x value lies between left to right. So x is minus half y, and it is root y. So it is going to be what? Half y less than or equals x less than or equals under root y. So your integral d x square plus y square dA is going to be integral 0 to 4 integral y upon 2 under root y x square plus y square dx dy. So this would be integral 0 to 4 x cube upon 3 plus xy square over this. And when you do the calculations and simplifications, you will get it to be y root y upon 3, and when you substitute here, it is going to be y square root y, and this is y cube upon minus y cube upon 8 multiplied with 3, that is 24, minus y cube upon 2. So this is what we have. This you will have to integrate with respect to y and do the simplification. In both the things you are going to get the same result. Okay, and the next problem is what? Here we have y is equal to x minus 1, and actually I think I don't need to go to GeoGebra to plot this one. Here you may very well see that, just a minute, let me make use of highlighter with this color. Yeah, when you try to look at it as a type 1 region, your x value lie between minus 3 to, so if you make use here, actually it has to be a straight line that you can do and see your x value is going to be 5. Okay, so it is 5. So your x ranges from -3 to 5. Fine. Whereas if you look at the lower and upper curves, your x minus 1 curve is the lower and under root 2x plus 6 is the upper. This is one way. And the other way, uh, if you see your y ranges from minus 1, sorry, your y ranges from -2 to 4. And x ranges, x, the lower curve is y square minus 2 minus y square upon 2 minus 3, and right curve is y plus 1. Okay. Comparing these two things, if you handle this problem by considering it as a type 2 region, it would be easy. Just because here things are clear, whereas here it is coming here, we may be in a doubt whether in this region whether to consider this part as the lower one or this part as the lower one. These kind of confusions may occur. In order to avoid these confusions, better we shall go with type 2 region, and that is exactly done in this problem by our author. Fine. So okay, let me show you the region as well. So if you go to this and so the curve z is equal to xy is the curve like something like this. Okay, and y is equal to x minus 1 and y square is equal to 2x plus 6. This is the region that we have. Here you may see the point of intersections. So exactly this region is the one that we have seen there too. So let me enable them to. So we'll have to rotate and see the common region. Hope you can see the common region now. And also notice the axis. So this is in the positive sense, this is in the positive sense, this is also in the positive sense. In the positive sense, we'll have to mark the common region. So once you mark the common region, you get the volume of this region, volume of this solid is the one that we are trying to find. Okay, by looking at it and trying to find the volume is not that easy just by doing the volume formula and all, because it is some unshaped region. Now by the help of integration it is easy to do so. So yes, we have to find out integral d xy dA. Here what is rd? It is the collection of points in R2 with y ranges from -2 to 4, minus, and x ranges from -3 to x ranges, sorry, y square upon 2 minus 3 to y plus 1. So it is y square upon 2 minus 3 to y plus 1. So this is our region D. So your integral d xy dA, this is becoming integral -2 to 4 integral y square upon 2 minus 3 to y plus 1 xy, first with respect to x and then with respect to y. That is how we have done things. So this is -2 to 4. When you integrate with respect to x, it is going to be x square y upon 2 to y square upon 2 minus 3 to y plus 1 dy. So it is integral -2 to 4. When you give x as y plus 1 squared multiplied with y upon 2 minus y square upon 2 minus 3 whole square multiplied with y upon 2 dy. Okay, so it is my integral minus 2 to 4. When you do it by the binomial expansion, y square multiplied with y, so it is y cube, plus 2y multiplied with y, it is 2y squared, plus 1 multiplied with y, it is y upon 2, minus here y square upon 2. So when you square it, it is going to become y power 4, and when you multiply it with y, you are going to get y power 5 upon, you have squared it, so you have upon 4, and actually you have minus, and when you take this minus inside, you are going to get plus. 2 times of 2 and 2 gets cancelled, it is going to be 3y squared, and you are multiplying that with y, so it is going to be 3y cube. Then this 3, when you square it, you are going to get 9, and 9 multiplied with y gives you 9y upon 2. So it is integral minus 2 to 4 y cube plus 2y squared plus y upon 2 upon 2 upon 2 minus y power 5 upon 8 plus, actually when you write this way, you would have minus here and plus here, yes. So this is going to be plus 3y cube upon 2 minus 9y upon 2. So integral minus 2 to 4. Let us write termwise. Y upon 2 minus 9y upon 2. So when you subtract it, you are going to get minus 8y upon 2, which is minus 4y. Okay. Next is y squared term. We have only one y squared term. So, um, so it is 2 gets cancelled, plus y squared is the thing that we have. Then the y cube term is y cube upon 2 plus 3y cube upon 2. So when you add it, it is 4y cube upon 2, which is 2y cube. We do not have any y power 4 term. And we have y power 5 upon 8. When you do the integration, it is going to be minus 4y square upon 2. So this shall be written as minus 2y squared plus y cube upon 3 plus 2y power 4 upon 4, which is y power 4 upon 2 minus y power 6 upon 48 minus 2 to 4. So when you give the limits, minus 2 times of 4 square is 16 plus 64 upon 3 plus 64 multiplied with 4, 256. Am I right? So 64, 16 minus, yeah, 256. I'm right. So it is 256 upon 2 minus, we have 4 power 6, right? So it is 4 power 6 upon 48. Let us write this way itself. And then minus 2 times of minus 2 square, which is going to be 4. And then minus 2 whole cube. So it is going to be minus 8 upon 3 plus 16 upon 2 minus minus 2 power 6 or 2 power 6, it is same, it is 64 upon 48. We'll have to just simplify it. I leave it to you people. So the next problem that we are going to see is to find the volume of the tetrahedron bounded by the planes x plus 2y plus z is equal to 2 and these things. Here I'll just show you the ideology. So we'll have to take everything in the positive direction. So I think Yeah, this will give you a clear idea. No, it is in the negative. So this way. Exactly. Yes. So here you are seeing something, right? So this is the region. This is the volume that we need to find out between all these curves. Okay. And excuse me. So things are plotted. When the things are plotted, and from this you may very well see your x value lies between ranges from 0 to 1, and y ranges from, actually this is x is equal to 2y. So from this you will have to write down what is y. Y is what? Half times of x. To this one, what is this? This you may note down from this one. Okay, we are plotting these things on the xy plane and seeing. So on xy plane z value is 0, so you have only x plus 2y is equal to 2. From this you deduce the value of y and you get this one. Okay, all these things are explained in this. That is what I have told you in a simpler way. We'll have to project the tetrahedron on the xy plane. When you project things on the xy plane, your z value is 0. So what you have is only x plus 2y is equal to 2. From that you will have to deduce the y value. So that is where your region ranges. So your integral over d x plus 2y plus, sorry, from this you'll have to deduce what is z, right? So from this your z is 2 minus x minus 2y. So integral 2 minus x minus 2y dA is going to be integral 0 to 1 integral half times of x to 1 minus half x 2 minus x minus 2y. First integrate with respect to y and then with respect to x. So integral has turned into this, and this is integral 0 to 1. It is 2y minus xy minus, sorry, actually with respect to y we are doing, right? So it becomes y squared x upon 2 to 1 minus x upon 2 dx. So it is integral 0 to 1. When you substitute these things, it is 2 times of 1 minus half, in the sense it is going to be 2 minus x minus, you will have to multiply this quantity with x. So it is minus x plus x square upon 2 and the square of this term. So it is 1 minus x square upon 4 plus x, right? And we'll have to substitute this one. Minus y is equal, this gives you x, and here this will give you minus of minus becomes plus x square upon 2, and this is also minus of minus becomes plus x squared upon 4. If you see here, you can see some terms getting cancelled, and we are left with what? Integral 0 to 1. So 2 minus 1 is 1. You have minus x, again minus x here, so minus 2x plus x squared, actually half times of x squared plus half times of x squared, and that gives you x squared, and excuse me. So this is what you'll have to integrate with respect to x, and that gives you x minus x squared plus x cube upon 3 over the limit 0 to 1, and when you do it, it is 1 minus 1 plus 1 upon 3 minus 0, so it is going to be 1 upon 3. So here, this is a quite interesting problem, I would say. We are directly asked to evaluate this integral. From the integral itself, we will deduce the information that x ranges from 0 to 1. So x ranges from 0 to 1. We have plotted these things. And y ranges from x to 1. So y is equal to x is this line, and y is equal to 1 is this line. So we have found this region. Okay, if we can do the integration directly with the help of this, it is good. Okay, else we may think it in the other way. It is a type 1 region. We'll try to convert this to a type 2 region. If we have to convert it to a type 2 region, y ranges from 0 to 1 and your x ranges from what, 0 to y, right? So you can rewrite your region in this way as well. Convert it into this way and try to integrate it, because when you try to integrate with respect to y to this function, if you have sine y, it is well and good, we can do it, but we have sine y squared. Okay, we cannot do the integration directly. Just by the given integral we have drawn the region d, and we have reformulated it to a type 2 region, and we are going to integrate it. Here if you see, first we'll have to integrate with respect to x, but the involvement of x is not there. So we'll treat the sine y square as constant and do the integration. So it is going to be y times of sine y square minus 0. Right? So if you take your y square to be some function t, then your 2y dy would be what? Dt. So you have this y dy that shall be rewritten as actually by this substitution, your this integral becomes integral y ranges from 0. Okay, I think I'll have to write it little bigger. Integral y ranges from 0 to 1, and this becomes sine t half times of dt. So this is what integration of sine t is, simply cos t, and your t is y squared 0 to 1. Just do it and you get this result. Quite simple, right? But here we'll have to make use of the ideology that from the given integral itself we can draw the region. That idea has to come to our mind. Next, these are some properties of double integrals. That is, if you are adding and performing the integration, it is same as that of the performing the integration and then adding, and then the scalar multiple rule and the inequality preserving. And if you have if you can split the entire region d into a sum of two regions, then the integral over this d is same as that of the integral over sum of integral over d1 plus sum of integral over d2. These properties, and this is another property, that is integral over d 1 dA is going to be the area of the domain. So this is one thing. And if you can find the supremum and infimum of the function f, then supremum times of area of the domain is the lowest possibility for the integral, and the sorry, actually m is the infimum. I have said the infimum and thing. This is the minimum value. Infimum is some minimum value. This is some okay. Maximum value is the supremum value. That is, out of all possible maximum values, the lowest among that is called as supremum. Okay. Out of all possible minimum values, the greatest of the minimum values is called as infimum. I have said infimum and supremum. If you know the terms, it is well and good. If not, I just clarified these things to you. This property is also satisfied. This property is useful in calculating some estimates. Okay, here in this problem we are asked to find out the estimate. It is quite difficult for us to calculate the exact value of the integral. In those cases we can find some estimates. How are we doing it? If you see, your sine ranges from -1 to 1, that we know for sure, and the similar goes for cos as well. So when you make a product of these two things, then also it is going to lie between -1 to 1. It cannot go beyond it. So if this is going to happen for sin x cos y, then what is going to happen for e power sin x cos y? Since your e power x is a monotonic function, okay, this is what we are going to have. and your D is the disk. Now, here comes the main thing. Actually, we have found m less than or equals f of xy less than or equals m. In this, we have found the big M and small m. Now, we will have to find out the area of the region. Here, D is given to be the disk with center, the origin, and radius 2. So, it is a circle with radius 2. So, pi 2 square is going to be the area. So, if you know the area, just multiply it with the minimum value, that is 1 upon E, and multiply it with the big M, that is E. So if you multiply this 4 pi with these two things, you are going to get the estimate for this integral. So with which we have come to the end of our discussion on double integrals over general regions. In the upcoming lecture, we are going to discuss about the double integrals in polar coordinates. Thank you.